Okay, so the we have quite a few things on the schedule today for to discuss on the administrative side of things. Um the quote of the day today, two quotes for today. Being Veterans Day, I figured these would be apt quotes for today. The first, this is kind of a hard quote to track down who originally said it, but as far as I can tell, this guy Richard Grenier maybe is the first one who said it, but it's kind of like a rephrasing of ideas from maybe Orwell and Kipling. But I like this phrasing better than theirs. We live in relative peace and comfort only because of rough men who stand ready, willing to do violence in our behalf. Uh, so, thanks to the veterans and folks who are actively serving, allowing us to be here and, peace and comfort and so on in our own homes and attend class and not have to worry about things like we see, going on in so many places around the world. And another quote by John Adams, again, kind of appreciating the fruits of the labor of our veterans and other folks. Um, and this is I cut out some parts because it's a part of a letter of his. Um, but he says, I must study politics and war that our sons may study mathematics and philosophy, etc., commerce and agriculture, and so on, in order to give their children the right to study painting, poetry, and music. So in some sense, we have to have folks who study the use of violence to create a structure where we can use something like logic to better our society. We have to have that baseline of safety first. We use logic to better our society, and we get ourselves to the point where we can, where we have enough surplus that we can study things that we enjoy for the sake of enjoying them, perhaps like painting, poetry, music, etc. Um, I would maybe argue that philosophy really kind of belongs in all three of these categories, but that's a maybe a moot point. Um, yeah, so that is the quotes of the day for today. Uh, thinking about Veterans Day today, and then I also have friends who are Marines, so they always like to say, the Marine Corps birthday is one day before Veterans Day, and you know, uh, just fun whatever rivalry between the branches. But I have lots of friends who were Marines, but not as many who were in the other branches. So a couple family members in the Army or that had been in the Army, and a couple that had been in the Navy, but uh, nobody was a fighter pilot though, so no Mavericks that I know. All right. So the other important announcement for today is the Unit 2 exam is this week. So that covers chapter 4 through chapter 6, so including chapter 5 and Bayes' theorem. It is due this coming Sunday, but do not wait until the last minute. Just like the Unit 1 exam, there are no due date extensions. So I would strongly plan on taking it Thursday night at the latest. And that way, if anything does go wrong, if there's a tech issue, a power outage, whatever reason, things don't go to plan, you have a full weekday as a buffer to, to either sort things out or to come up with an alternative plan. Pop onto a CCAC campus or something, use the resources there if needed, something like that. If you wait until Sunday or even worse, Sunday evening, your resources are really limited. So, don't wait until the last minute. Uh, I think at this point, most folks have taken the examine practice exam, but if you haven't, I would recommend doing that as soon as reasonably possible, if at all possible, maybe like right after class today, get that knocked out. It shouldn't be that difficult of a process. I did post several different resources, one of which the detailed examine user guide that's on Blackboard, um, I think should be, extremely helpful. It should walk you through all of the steps. So, make sure to get on. And that examine practice exam, remember, is only for the purpose of practicing the examine, process for getting logged into examine, getting an account created, figuring out how to get the browser extension installed, getting the test up and running, the password transferred over, all of that. There is also a sample Unit 2 exam posted on my stat lab. So that was posted late last week. I want to say maybe, was it Thursday that I had that up? I think Thursday night. So that is available, and that's the review, the Unit 2, the sample Unit 2 exam is the review of the academic material for the Unit 2 exam. So that's the one where you should go through, take it as if you were taking the actual test, make sure that you're comfortable with all that material, or if you come across something that you're not comfortable with, reach out to me, review lecture notes, review the homework problems, anything like that, um, to fill in any of those knowledge gaps. And then also, let me switch my share here really quickly and just go to full screen. Also on Blackboard, under exam material, I posted a couple additional documents, the exam 2 formula sheet. You can use the formula sheet 1 page front and back on exam 2. Here's an example of one you can use. You can feel free to just print this off and use it, or you can even use it as a PDF or something on your screen. That's fine if you prefer that. If you want to, use this as a base and add to it, that's fine too. If you want to make your own, that's certainly fine. That's probably even preferable. It's usually better to make your own formula sheet because you kind of know where everything is then. It's phrased exactly how you like it to be phrased. And frankly, a lot of times if you go through the effort of making your own formula sheet, you review all of the contents of those chapters that are on the exam. A lot of times if you make your own formula sheet, you don't even need the formula sheet then because you've already kind of reviewed all of those formulas, taken the time to curate them, to write them down, understand them a little better and all that. And, you might not even need the formula sheet at that point. Always nice to have it if you do need it, but that's one of the benefits of making your own. There's also the normal table on here. Of course, you can use the normal table, so you can print this off or use it as a PDF. You can use that either way, printed or electronically. Of course, make sure that you get both sides. If you do print it off, make sure you get the positive and negative sides. I guess in theory, you maybe could make do with one side, but probably a lot easier to have both. Oh, and there was one more thing under supplemental material. I think we'll get close to finishing up confidence intervals today. So my cursor just froze for some reason. There we go. So I made available this folder on Blackboard under supplemental material, chapters 7 and 8. And there's some, again, like just practice supplemental problems. These aren't to be handed in or anything. There's some additional material in here we might talk about this time or next time. But this hypothesis testing narrative, it's a scan of an old book, Friedman's Statistics. And this is probably the best narrative introduction to what a hypothesis test is, what we'll be studying in chapter 8, that I've come across. So I made one little note here to some wording that I wasn't super happy with, but you'll see that here's kind of like part 1 starting here, introduction, was it just due to chance, etc. Go to the next page, that's part 2. And then up here at the very top is actually the end, the third part. I put them together like this so that when I print them off, in a physical classroom, it kind of prints on the front and back of one piece of paper, and you can follow along that way. But go 1, 2, and then 3. We'll probably quickly read over this next time as well, but I would recommend reading over it before next class. Should only take a few minutes. But much of the challenge of hypothesis testing is the logic behind it, not so much the mathematics. The mathematics is stuff that we've seen already, but it's the logic behind it. It's what do we do when and why do we do that at that point? And this gives, I think, some really good insight into it. So I would recommend, because hypothesis testing is more challenging, reading through this just to get a narrative introduction to it, and maybe even skimming the beginning of chapter 8. And it might not be a bad idea to, even after next class, go back and do the same thing again. Reread this narrative, skim the beginning of chapter 8 again. Do that a couple of times until that logic really kind of makes sense. The logic is a little backwards of what we would expect. It's kind of like an inverse problem, or it's really more like an argument by contradiction. Okay, so let me get my windows resorted out here. All right, and then the plan for today is just to continue with chapter 7. I think we have one more problem on confidence intervals for proportions, and then talking about our next two confidence intervals for the mean when standard deviation is unknown, and confidence interval for variance and standard deviation. And while I am thinking about it, I'm going to post 2 additional tables in the chat. I think we'll get to both of these today, but if not today, then next time. So one is the chi-squared table, the other is a t-table. I just posted those in chat, so if you want to drag them to your desktop just so that you have them available. We'll be using at least the t-table and probably the chi-squared table later this class. So, you don't have to worry about opening them up or understanding them yet. We'll get to that, but just so that you have them available. Okay, in the next class, depending on time, how much time we take today, we might cover bootstrapping next class, or I might kind of punt that to a lecture recording, and then we will definitely get a start on chapter 8, hypothesis testing. So, and I guess one last little note. I mean, I know there's been a lot of administrative stuff all at once here, but one last little note, I suppose, is so we have Thanksgiving break coming up in a couple weeks. And actually, Thanksgiving is quite late this year. I think it's as late as it can possibly be, isn't it? Isn't it like always the 4th Thursday of November or something? And like November 1st was a Friday, so it's like the latest in November can possibly be. And that basically means I think, let me double check the course schedule so I'm not saying anything wrong. Yeah. So that basically means that we come back from Thanksgiving break, we have 1 week, and then we're immediately into finals week. So, depending on your class meeting days, you might meet that Monday or might not, but yeah, we basically like have 1 week of classes and then we're right into finals week. So, we're already kind of starting the run up to the final exam at this point. So, it is a bit of a slog in the fall, and especially when Thanksgiving falls so late like it did this year. But just be aware of that, after you finish the Unit 2 exam, and really maybe even during this week, kind of have that, start turning on that final exam mentality, right? Start turning on the end of semester mentality where you're thinking like, okay, well, what exams do I have? What semester papers or projects or labs or whatever, do I have that are big things due at the end of the semester? How am I gonna, manage all of those demands at the same time? So start thinking of that now. Usually we have Thanksgiving and then there's like maybe 2 weeks or so until finals week, gives you a little bit more of a buffer, but start thinking of that this week and next. Start looking ahead to final exam week because it's going to be here before you know it. We have Thanksgiving week and then it's, you turn around and final exam week is here. All right. So just a quick reminder, the central limit theorem that formed the basis for our confidence intervals. I'm not going to really go over it, but it's just there to remind us of that. And our confidence intervals, particularly when we had a confidence interval for the mean, when we knew the population standard deviation, we noted that X bar is a good estimator of mu, which basically meant we wanted a symmetric confidence interval. In other words, I don't want to systematically give a confidence interval that overestimates where I think the mean is or underestimates it. So X bar should be right in the middle of the interval in some sense. Same with p hat being a good estimator of p when we compute the confidence interval for population proportion. Same thing, it should be symmetric. And later on today, when we see confidence interval for variance, we'll also want, in some sense, the variance, the sample variance, to be kind of in the middle of the confidence interval. We wanted the confidence interval to maintain some kind of symmetry around the variance. The symmetry for the variance is a little bit more complicated or nuanced, but it is still a similar idea. And remember, the idea behind confidence intervals is, well, our best guess at, for instance, mu, the population mean, is x bar that we compute from a sample. But how good is it? If I just say my best guess is x bar, that might be a really good guess. I might be quite confident that x bar is going to be pretty close to mu. Or that might be, there might be a lot of error there. It might be a pretty terrible guess. So we compute our confidence interval for the mean once the standard deviation is known. This way, we have x bar observed, the x bar that we get from our sample data. This could either be we actually compute it based on some data that's given to us, or in the problems that we've seen so far, we're just told x bar observed is this number, right? We could take an actual sample, go back to chapter 3 and compute x bar if we wanted to, or it could be given in the problem just basically to save time. And then we want to go x bar plus or minus a margin of error, and this is what gives us the kind of buffer to be able to say that we're a certain amount confident that this interval covers the true mean. And that margin of error looks like a z-score, a z-index, times the standard error, sigma x over root n. That standard error coming right from the central limit theorem here, sigma x over root n. So all of this ties together very nicely, right? And we saw similarly for a confidence interval for P, a population proportion, probability of success, probability of an event, something like that, is P hat, or if we wanted to be a little more specific, this is P hat observed. But kind of since we're in probabilities, we're, we already have a P and a hat and didn't write too many different things, but I wrote it a little more explicitly down here. So this is P hat observed plus or minus, again, a margin of error, which looks like a z-score times root P hat Q hat. That's like sigma. That's our standard deviation for a binomial over n. Okay, so then continuing on. So that was just a really quick recap of what we had gone through up to this point. And so continuing on, a little bit late for the election at this point, but an example. So suppose we're interested in knowing P, the probability a voter votes for candidate A. So we have some exit poll or something like that. We can conduct the exit poll between 3 and 4 p.m. on election day. And out of 979 people polled, 539 say that they voted for candidate A. So let's construct a 99% confidence interval for P. Okay, so what do I know? I like to start here. I think if nothing else, it just kind of helps us organize things in our head. Well, of course, we don't know P, probability the person voted for candidate A, right? That's kind of the thing we'd really like to know. If we had a perfect exit poll, we'd just be able to say at, 9 a.m. or something, oh, okay, this candidate's going to win or that candidate's going to win. But, we don't know this probability at the outset. What do we know? Well, we know P hat, which I'll put kind of in quotes, really P hat observed. Well, mainly that's because we know the number of successes, 539. We also know n, the number of trials, 979. The sample size, the number of individuals polled. And the other thing we know, trying to get everything on one screen here, is we know the desired confidence level. The desired confidence level, as we mentioned last time, this is a decision that would have to be made. This is an experimental design decision. We would say at the outset, before we collect any data or anything, my goal is to collect this data in this manner, using this questionnaire or this survey technique, whatever. And I would want to compute, say, a 99% confidence interval for my population proportion. That would be decided at the outset. We don't decide that we want a 99% confidence interval based on the result of the sample or right? We ought not do it that way anyway, even if maybe occasionally people do things like that. There's an idea called p-hacking that's kind of that kind of idea, and it's generally not a very good, reliable statistical technique. So we want to stay away from that. But this confidence level would be decided, and for practical purposes in a problem set or something like that, in a stats course, it would just be provided. We decided on the 99% confidence level. And this impacts our Z alpha over 2, our Z index. Remember, 99% is like the success rate. We're going to report an interval that 99% of the time, when an interval is constructed in that manner, it will cover the true population proportion P, and well, 1% of the time it won't. So alpha is our error rate, 1%. And that says that alpha over 2, the thing that comes up in the Z alpha over 2, the thing related to the Z index or the area in each tail, we might miss by P being a little higher than our interval, than our upper bound, or by P being a little lower than our interval's lower bound. So in each tail, we can miss higher, we can miss low. We have alpha over 2, error rate, or 1/2 of 1%, that's 0.005. So 1/2 of 0.01. So there's a lot of stuff we know. There's only one thing we don't know. Now, of course, if we knew what P was, the population proportion, the actual probability of voting for candidate A, we would just say what that is. We wouldn't have to do all of this confidence interval silliness. The issue is that we have a sample statistic, P hat observed. That's an estimate for P. But there's going to be some sampling error here. In this sample, we might have gotten a few extra folks who like candidate A than maybe would be typical, or maybe a few fewer folks who like candidate A than would be typical. So we have to account for that sampling error, and that's really all the confidence interval is doing, is accounting for that sampling error. The fact that we took a small sample instead of sampling the entire population. So there could be some sampling error. Okay, so now I plug into my formula up here. I know that P hat observed is the number of successes over the number of trials, 539 over 979, and jumping over to the calculator to do that. I know this isn't on the screen, but we just have just a simple division here. So this gives me about 0.55. We'll just go with that. So P hat observed is 55%. If I said, what's your best guess at the number of votes the candidate A is going to get, or the percentage of votes, or what's your best guess at what P is, the population proportion, the best guess at this point would be 55%. Is that a good guess? Is it like 55% plus or minus 1 percentage point? In which case we're pretty confident that candidate A is going to win, because if candidate A gets 54 to 56% of the vote, of course they're going to win. Or is that like 55% plus or minus 15 percentage points, like 40 to, 70%? Well, then it's kind of still a toss-up. If candidate A got 40% of the vote and candidate B got 60%, well, pretty clearly it could go either way. So that margin of error is extremely important. As kind of a side note, when pollsters like Gallup polls or these reputable polling agencies perform these polls, they typically try to keep the margin of error down to maybe a few percentage points, maybe something like 3 or 4 percentage points. So typically they're not taking surveys that are so big that they're down to like, 0.5 percentage point or 1/10 of a percentage point. because you need to kind of scale your sample size quadratically. So if I want to cut the margin of error in half to make 1 over root n 1/2, I need to quadruple. I need 4 times my sample size. To cut the margin of error by a factor of 100, I need 10 times, or sorry, to cut it by a factor of 10, I need 100 times the sample size. So I need a much larger sample size to get, a moderate impact on my margin of error. So a lot of times you'll see these polls that are like plus or minus, say 3 percentage points, something like that. And for a close race, if you're saying that this person's winning by, 51.5 to whatever, plus or minus 3 percentage points means it's still a toss-up, right? Okay, so we have p hat observed, 55%. And now I want to compute my lower and upper bounds. So we're going to take p hat observed as our anchor point, as our center, and go plus or minus a margin of error from there. For my margin of error, what do I need? I need a z-score, a z-index, times my standard error. I need a z-index. Let me just make a space for that and come back to that. Times my margin of error is square root of p hat observed times 1 minus p hat observed, or that's 0.55 times 1 minus 0.55 is 0.45. And then still under the radical is our over n, our sample size of 979. And the same radical is multiplied by the z-index in the upper bound as well. I'm not going to rewrite the whole thing, but that's what it is. Now I need to find z alpha over 2. That's my last little bit that I don't have. I need to find a z-index. Here, alpha over 2 is 0.005. Remember, the z-index we're looking for has area alpha over 2 to the right of it. It's not like we find some z-index and then we divide it by 2. This over 2 is attached to the alpha. We have the area because we have 2 tails. We have one over here as well. We're looking for the tail with right hand area 0.5%. And there are 2 ways I can approach this. I can either approach it by, say, complementary event. This is the 99.5th percentile of z. So that would be the area to the left of z alpha over 2 would be 0.995. Or we could use symmetry and say that negative z alpha over 2 has 0.005 area to the left. Either way is fine. I don't really have a preference, even myself, one way or the other. Let me swap my share over here real quick. And since we're on the left tail over here, since we're on the negative z-score left tail, let's just flip over. And so we're looking for 0.005 area to the left, and that would be related to negative z alpha over 2. So I want area to the left of 0.005. Be a little bit careful. Don't grab like this one by accident. That's got too many zeros in it. So 0.005, 2 zeros, then a 5. And that's one of our special cases. It falls right in between these two, 0.0051 and 0.0049. So let's follow this down and over. And I see that the area to the left of a z-score of negative 2.575 gives me an area, a tail area of about 0.005. So it's negative 2.575. That's what negative z alpha over 2 is. So z alpha over 2 is 2.575. Note that in these symmetric confidence intervals like this, I mean, if you forgot to change the sign, if you put negative 2.575 in here, I mean, you still get the same two numbers for your lower and upper bounds. They're just flip-flopped, right? Your lower bound would actually be your upper bound, and your upper bound would actually be your lower bound. But so if you forget that sign change, it's not a super big deal, but we do want to get it right because in the future, we'll see that, we can have one-sided confidence intervals, and then we have to be a little bit more careful. But if you made a mistake and forgot to get rid of that sign, in an example like this, you're not going to get the wrong answer. You'll just have to flip your lower and upper bounds. Okay, and now we just have to plug all this in the calculator. So I have what, 0.55 minus 2.575, that's my z-score, times my standard error, which is a big square root of all this stuff, 0.55 times 0.45 over 979. And parentheses for the square root, double check, 0.55 minus 2.575 times the square root, that looks good. And this gives me 0.509 or so. So this is about 50.9% for the lower bound. And then if we want to compute the upper bound as well, I do second enter. So that pulls out my previous entry, and I can just navigate back to the minus sign and switch that to a plus sign, and that gives me my upper bound, 59.09 or maybe 59.1%. And now I can say something like my 99% confidence interval for P, or the probability of somebody voting for candidate A, is 50.9% to 59.1%. And we do see that in any of the values of P that fall in this interval, this 99% confidence interval, candidate A wins. So at this point, we might be comfortable calling the election for candidate A, well, at least just based on the mathematics. So at this point, our confidence interval question is done. We're happy with this. But a couple other questions. So question B is more of a experimental design question. I think it's always good to kind of think back to this every once in a while. It's not really the focus of this course. It's not really the focus of this course to go into all these experimental design things. We're mainly looking at the math, but it is good to just keep this in the back of our minds, especially in things like this that are very applied and that, are kind of big in the news today, right? The ability to predict elections seemingly has gone off the rails a little bit in the decade or so. So having a little bit more well-rounded understanding of, okay, yeah, the math looks good, but what are some other things that could be going on? So question B, or part B of part 4, or question 4, simply considering the statistically calculated on the basis of the exit poll, can we call the election for candidate A? And that's what I said down here is, yeah, I mean, just looking at the math, we probably could confidently call the election for candidate A, right? This is a 99% confidence interval, so this is even a wider interval than we would get for, say, a 95% confidence level. We're even more confident about this interval. And we see that any value of P, the probability of a voter voting for candidate A, or essentially the proportion of overall votes candidate A will get, any one of those, any value of P that's in this interval, candidate A gets 50.9% of the votes or more, candidate A is going to win under any circumstance in this interval. So we probably could call it for candidate A. A really important question. Simply considering the mathematics, the statistics, the calculations. Do we care what the size of the population is? Did the size of the population enter into our calculations anywhere in here? If we were doing this exit polling for a local small town mayor in a city with 5,000 residents, and we sampled roughly 1,000 of them, or if it was a state governor and we have whatever 10 million or something residents, or if it was the US president, we have something like 300 million residents. I don't know how many are voting age or whatever, but just more or less, you can see that there are many orders of magnitude different here. Would we say, oh, well, I'd feel comfortable calling, the local mayor election with just 979, a sample size 979, but I wouldn't trust the math for as much for a governor, and I wouldn't trust the math at all for a president because that's a small sample size. Just according to the math, no, that doesn't matter at all. We've accounted for the sampling error here. The only thing that we really care about as far as n goes is n is bigger than or equal to 30. It follows that rule of thumb. So n of 979 is definitely good enough for us to apply the central limit theorem results under that rule of thumb and set all of our confidence intervals on solid ground. Sorry, brain malfunction there. We're in the binomial, the confidence interval for P scenario. So we have at least 5 successes and 5 failures. Again, that was our rule of thumb here. 5 successes and 5 failures. So we're happy calling the election on the basis of this, whether it's the presidential election, the local mayor election, the state governor election. The size of the population doesn't matter as far as the math goes. Now, part C is where the interesting discussion comes in. Well, should we call the election on the basis of this sample? Are there considerations other than just the numbers, just the mathematics and the central limit theorem and so on that might be important? And the answer is, I think, yes, there are a lot of considerations that are important, and it's good to just, remind ourselves of this every once in a while. I try to bring some of this up every once in a while. Again, not the main thrust of the course, but should we call the election on the basis of the sample? Probably not. If it was the local mayor and we have, 5,000 residents and we've got 1,000 of them counted already, and probably only 2,000 to 3,000 are going to vote anyway. Yeah, this is probably a representative sample. Remember, that was an important idea way back in chapter 1. Do we think that we can get a representative sample of 300 million people in a sample of size under 1,000? I'd be less confident about that, right? Can we get the thoughts and sentiments and so on of the eastern side of the country versus the western versus the southern side of the country, or all of the different age demographics, or the different party affiliations, or all of the different, this or that, whatever way you want to slice and dice the population? Can we kind of get some people in each from each of these boxes in our sample? Well, there are so many ways to slice and dice 300 million people. I mean, I don't think a sample of size 1,000 would do it. Maybe a sample of size 1,000 would be enough to say call a governor election or something if we think there are going to be, maybe 1 million people voting or something like that for it. Maybe that would be a little more, it's a little more geographically restricted. You're kind of all in the same state, right? So that might be a little bit of a different story. So practically speaking, do we care about the size of the population? Yeah, we do, because how can we get a representative sample of an enormous population with a relatively very small sample size? It will be more difficult to do. The other thing is that we probably have a pretty biased sample, right? If we're looking at an exit poll conducted between 3 and 4 p.m. on election day, well, Are we considering the early voters or the absentee voters or any of that? They might lean one direction or another. Are we considering people who voted early in the morning or late in the evening? Is there a lean towards one affiliation or the other for different times of day? Um, so there are a lot of practical reasons why we shouldn't call the election, even though kind of the calculation itself says, if we just looked at this blindly, it says we can be quite confident in a sense that candidate A is going to win the election. We should probably hold back for all those reasons. Any questions on, yeah, any questions on the first three parts of this, the calculation or those follow-up points? So I actually think that part B is, in some sense, maybe the most stunning of the parts of the discussion here, that, as far as the math itself is concerned, not thinking about, representative samples and things like that, or bias samples, but just the math itself, the size of the population doesn't come into the margin of error or the confidence interval anywhere. Nowhere do we see, blah, 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 and the population is 3 million people or 300 million people. We only have the size of the sample coming in. So the size of the sample is the only size, in a sense, that determines, that comes into the calculation for determining a margin of error. Whether it's a population that's only a little bigger than our sample, or whether it's a population that's thousands or millions of times as big as our sample, it's the same calculation, right? The only question is, when we come all the way back up here, there we go. The only question is, this central limit theorem, this normal distribution, what is the convergence of X bar to the true mean? What does that look like? And that looks like a function of the sample size. X bar is going to get close to the mean, like 1 over root n, whether your population is 1,000 or 1,000,000 or 100 million, X bar gets close to the mean at the same rate as sample size increases. So it's kind of almost like a magical property, right? Like, that it doesn't matter if we're, from the standpoint of the calculation, if we're making an estimate about a small population, a medium size population, or a huge population, the same sample size kind of has the same effect on estimating the mean or estimating the proportion, whatever it may be. Okay, and then let's work on part D here, a last calculation example. What sample size would we need if we want a margin of error of at most 1 percentage point? So maybe we come down here and say, okay, 50.9% to 59.1%, that's nearly a 10 percentage point swing from the bottom to the top. Maybe I'm not quite happy with that. I guess it's a little closer to an 8 percentage point range from the bottom to the top. I'm not quite happy with that. I would really like to have margin of error at most 1 percentage point to tighten this down a little bit. What can I change here? Well, I certainly don't want to change my confidence level. I don't want to say this is too wide of a confidence interval. I'm just going to make myself less confident so that I can report a smaller interval. That probably wouldn't be a great practice. I can't really change my p hat observed. I mean, that's just my sample proportion. So my only lever that I have to pull is my sample size. If I want a smaller margin of error, a tighter confidence interval, then I need a bigger sample. To maintain the same level of confidence and give a narrower range of options, I need a bigger sample so that I have a more informative sample. We're also assuming that p hat observed remains the same here. Of course, as we take a larger sample, if I said, okay, we got these 979, we need a bigger sample, go on and sample more folks. Well, of course, p hat could change. P hat probably will change. from when we go to from our small sample to a much larger sample. But here we're going to assume that p hat observed stays at this same proportion of wherever it was here, 55%. So that's a pretty big assumption we're making, but we actually will see that it's not really a terrible assumption. This p hat observed times 1 minus p hat observed, this margin of error bit is maximized when p hat observed is 50%. And being 55%, we're pretty darn close to that. So if p hat observed were to increase, if it were to go to, say, 60%, our margin of error would actually decrease even more than we had anticipated from the larger sample size that we compute in D. If it were to go down from 55% to, say, 52 or 51%, if we're to get closer to 50%, I mean, my standard deviation might go up a little bit, but it's not going to go up a ton, right? I might miss the mark of 1 percentage point by a teeny bit, but I'm not going to miss it by much. So I'm not super worried about that. Now, if I had, 99% of people voting for candidate A, well, 1 minus 0.99 is a very small number. And if that 99% comes down to like 80%, well, then I might have a really substantial increase in my standard deviation here. I might want to do something more conservative and, suppose that p hat observed is 50%, something like that, for the purpose of computing this margin of error. But that's a little outside the scope of this problem. Here, we're just assuming the p hat remains the same. What n do we need to get a margin of error of at most 1 percentage point with, of course, the same confidence level? So we want a 99% confidence level and the margin of error less than or equal to 1% or 0.01. Well, what is my margin of error? My margin of error is this stuff. My z index only depends on alpha. It only depends on the size of these tails, right? It only depends on my confidence level. My z index doesn't change when I change the sample size. I've already computed that as 2.575. And then I have square root of, well, we assumed that p hat observed remains the same, so we don't have to change the numerator inside the square root. That's 0.55 times 0.45. Over n. N is the sample size that we are trying to find. What sample size do we need? Oh, so that this number is less than or equal to 0.01. I see that I can divide by 2.575 and square both sides. Less than or equal to. So I divided by 2.575. I square both sides. I don't have to switch the direction of the inequality. I didn't do anything. I didn't divide by a negative, anything like that, so I'm still good. And now what I would do is like invert top and bottom, but I do have to be a little careful here. If I invert, that's kind of like multiplying by n, dividing by 0.55 times 0.45, and then multiplying by the reciprocal of 0.01 over 2.575 squared. That actually does switch my inequality sign. So I have n over 0.55, 0.45, bigger than or equal to, which makes sense, right? If I pick a bigger sample size of bigger n, that makes it easier to satisfy this inequality. If I pick a bigger n, that makes it easier to satisfy this inequality pointing the other direction. So the logic also makes sense. So I invert on the left, I switch the sign, the inequality sign, and then I invert on the right. 2.575 over 0.01 squared. And I see now I just multiply through by 0.55 times 0.45. And I just need to plug this into my calculator. Let's come over here and do that. So I have 0.55 times 0.45 times, and all of this stuff will get squared, so parentheses, 2.575 over 0.01, and then all squared. That looks good. So this is 16,410 or so. Point 797, we'll do like that. And since we want to have a margin of error that's at most 1 percentage point, this is like the exact fractional cutoff. If I want a slightly smaller margin of error, I pick a slightly larger n. So I'll choose n to be at least 16,411. I'll always round up in this case. I mean, it's a bit of a pedantic thing, but it's the kind of thing that is really annoying on my stat lab or something. If you just round to the nearest integer, you miss the answer to the question by a tiny bit, half the time. So we'll always round up here so that we just make sure that we do have a margin of error that's at most 1 percentage point under the given assumptions. Does this roughly make sense? Well, we wanted to take a confidence interval that was about 8 percentage points wide, and we wanted to reduce it to an interval with a margin of error at most 1 percentage point, so 1 to the left, 1 to the right, so 2 percentage points wide. We wanted to reduce the size of our confidence interval by a factor of 4, and the size of our confidence interval goes like 1 over root n. So if I want 1/4 as wide of an interval, I need 1 over 16. I need to square root that to get a 1 over 4 out, right? I need n to turn into a 16n. I need my sample size to increase by a factor of 16. I started with a sample size in the ballpark of 1,000. My new sample size would need to be in the ballpark of 16,000. So that does make sense with what I would expect. So I feel confident that this is the correct answer. So it's not a trivial thing to just say, we have a confidence interval that's plus or minus roughly 4 percentage points. Just take a bigger sample and get it down to 1 percentage point. We need to do 16 times the amount of work. So we need 16,000 voters instead of just 1,000. Any questions on that? Any questions on either of the confidence intervals we've discussed so far? Confidence interval for mu when sigma is known, or confidence interval for proportion? Okay. Let's move on to our next confidence interval then. Now, nicely enough, this confidence interval is going to follow the same structure. I'm jumping a little bit ahead here, but this confidence interval is going to be x bar observed plus or minus something times standard deviation over root n. It's going to look quite similar to our previous confidence interval for the mean. Now, something we said previously was, well, in confidence interval for mean with sigma known, I mean, that's a little bit strange. Like, how often are we going to not know the population mean, but we will know the population standard deviation? That seems pretty unlikely. I mean, it could happen. The mean and standard deviation are kind of orthogonal in a sense. So you could know one and not know the other, but it seems kind of unlikely that that's going to happen in a practical case. So we were building up to this case that's a little more practical. Confidence interval for mu and sigma is unknown. So what is unknown here? Mu and sigma, basically all of our population stuff. And what is known here? Well, basically all of our sample stuff. We know the sample size n, we know x bar observed, our sample mean. We also know s, or s squared, whatever it may be, our sample standard deviation. And of course, we know alpha, our confidence level. We presume that that's given to us or decided in advance. Well, I have a little bit of a philosophical issue here, right? Here, I'm estimating two things, actually. I'm estimating mu by x bar observed, and there's going to be some sampling error in there. This margin of error accounts for the sampling error for when we estimate mu by x bar observed. The sample we got might have a preponderance of, smaller number of results or larger number of results or something. So it might throw x bar observed away off of mu by a little bit just by sampling error. And we account for that with this margin of error, z alpha over 2, sigma x over root n. Now I could say, well, my best guess, remember we're kind of pretending that S is a good estimator of sigma. I could just say, well, my best guess of for sigma is S. So just use this up here. Just use this confidence interval, the same one exactly as here, but replace sigma by S and be done with it. And actually, some textbooks do recommend that approach, but they say like, okay, in these scenarios, do it that way, and these other scenarios, do it this other way. I think that's way too complicated. There's a textbook, I think it's Mendenhall, it's a Cengage one, that a very good textbook. I really like it, except that they do it, they take that approach, and I'm like, that's way too complicated for a beginner course to say like, sometimes we can get away with pretending that we're not really estimating sigma by S when we are, and sometimes we can't get away with that. That's a bit too complicated. So kind of our knee-jerk reaction would be, just replace sigma with S, do your confidence interval like this, and be done with it. There's a bit of an issue there, though. Because we're also estimating sigma by S and mu by x bar observed, well, S could be a bad estimate of sigma, right? X bar observed could be a bad estimate of mu if we got a sample that had, say, if we were measuring heights, maybe a bit more shorter folks than we'd expect, or a bit more taller folks than we'd expect. Then X bar observed gets thrown off of mu. But also, if we got, a bit wider of a distribution than we'd expect, or a bit narrower of a distribution than we expect, S can kind of get thrown off of sigma. Our sample standard deviation might not be a great estimate of the population standard deviation in this case. There's more uncertainty. There's more that can go wrong. X bar observed could be far away from mu, and or S could be far away from sigma. We're estimating two things now. Either of these things could be kind of far away from their population value. There's more uncertainty. We really ought to account for that with a larger margin of error. We ought to respect the fact that there is inherently more uncertainty here because we're estimating an additional thing. We're estimating sigma by S. We ought to make the confidence interval a little wider, increase the margin of error a little bit to maintain that same level of confidence that we had before. Now, when sigma is known, the central limit theorem, another way to say it is that this quantity, x bar, meaning the random variable x bar, minus mu x bar over sigma x bar, sigma over root n, that's just kind of the z-score for the x bar distribution, right? For the one that the central limit theorem, that kind of popped immediately out of the central limit theorem. So when sigma is known, the central limit theorem applies and says that this thing, x bar minus mu x bar over sigma over root n, is standard normally distributed. Well, what do we get if we replace sigma by S? We get something that kind of gets the kind of reserved name T. So the same way that when we say Z up here, we're talking about the standard normal distribution most of the time. If we're in stats and we say T, at least in the context of things like confidence intervals and hypothesis tests, we're typically talking about this quantity here. It's kind of like a standard normal distribution. but it's a different distribution. It's a distribution that's called the student's T distribution. Uh, and often just called the T distribution. So a little bit of historical background here, just because it's kind of a strange name for it, like student's T distribution. This is students in the possessive case. So like the T distribution that is like owned in a sense by student, by someone named student. And the history of this, which we know now, but wasn't known at the time when it first came out, is that there was a beer master or whatever they call the folks who like taste the beer and make sure that it like tastes good for each batch. Um, his name was Gossett, I think William Gossett. Um, so he worked for Guinness Brewery back in the early 1900s, I think over in Ireland. And one of the issues with beer, with brewing beer, is that you're using natural resources. You're using like barley or hops or something, things that grow in the ground, and they might grow a little differently from one season to the next or from one crop to the next. So, maybe the soil's a little different, or there are more days of sun versus rain or whatever. And, the barley or the hops or whatever might be stronger or weaker, or more of this flavor or less that flavor or something. Or maybe the yeast, or right, there's a lot of inputs that go into making beer, and a lot of them are natural inputs. They're not just pure chemicals that are always the same. So when you come out the other side, how do you get a consistent taste in your beer when you have all of these inputs that are highly variable, and there are many of them, and you want to put them into this process and then kind of come out the other side with a very consistent product? Not an easy thing to do. Well, so this guy Gossett, their beer meister, whatever he's called him, I'm blanking on the name at the moment, but um, so he came up with the statistics, particularly for how to do this with small batches, right? I mean, in the Z distribution, we kind of leaned heavily on, in the central limit theorem in the Z interval, we leaned heavily on that rule of thumb that we have a large sample size, and that kind of, smooths out a bunch of the rough edges and makes things a little easier. Well, when you're making, huge vats of beer, you can't just say, well, let's just make 40 vats of beer. That might not be practical. So you have small sample sizes, quite variable inputs, and you want a very consistent output. How do you handle this? Well, basically, he did all the stats to figure out this T distribution. And then he published it anonymously, because obviously, like, this would have given Guinness a huge leg up on their competition, being able to produce a better end product with essentially better technology, the better statistical modeling. And he thought that, I guess, people should know about this, so he published it under the pseudonym Student. So the name of the person who published, or the name of the person who ostensibly published the paper that said, here's how the T distribution works, and here's all the math to support it and all of that, that was published under the name Student, and that's why it's Student's T distribution. And sometime later on, people figured out somehow, I don't know if he ever got in trouble or what, but they figured out who the guy was and what the story was. So that's why it's called the student's T distribution. It's like if you were to say this is Bill's T distribution, William Gossett, except he published it under the name Student, so it's student's T distribution. So the PDF for the T distribution, remember the PDF for the standard normal was this like exponential thing, e to the power stuff. The PDF for the student's T distribution looks like this. It's kind of a power law. It's like, let's just call the stuff in parentheses like more or less kind of like x squared or something like that, to a power. Trying to highlight the power over here. This little thing that looks like a V is typically the parameter nu. So the parameter for the T distribution is typically nu. The Greek letter N that looks like a kind of a curly V like that. And it's called the degrees of freedom. So that's its name. Its parameter is called the degrees of freedom, kind of like how the standard deviation, or sorry, kind of like how the general normal distribution has a parameter that's maybe the standard deviation that we write as sigma, or it has a parameter that's like the mean that we write as mu. This parameter here is called the degrees of freedom, and we write it using this Greek letter nu. We don't typically write nu, so, but in the tables, it's called degrees of freedom. It's, let me put this on the next line because that broke it in an annoying place. It often turns out that nu, the degrees of freedom, ends up being sample size minus one. Not always. We'll see some examples later on in the course where we have a different number of degrees of freedom, but quite often this ends up being the sample size, or this ends up being the degrees of freedom, the sample size minus one. Now this parameter nu, this parameterizes our family of functions the same way that if we take a general normal distribution and we change mu, it slides our distribution left or right. Or if we were to change sigma, it makes our distribution like wider and squatter or skinnier and taller. We get a similar thing for the t distribution. So the t distribution actually looks very similar to the standard normal distribution. There's not like a standard t distribution, like the t distribution basically is already a standard t distribution. So if I think of, let's say, the standard normal distribution, I'm going to try to draw this like reasonably well. You might have to use your imagination a bit. But in black here, we have z, the standard normal distribution, just as kind of a something to compare to. Now the t distribution, if the degrees of freedom is large, in other words, if the sample size, roughly speaking, is large, remember why we're using the t distribution. We're using t instead of z, if I can get this thing out of the way. We're using t instead of z because we're estimating the standard deviation as well. And particularly for small sample sizes, I mean, our sample standard deviation might not be very close to the population standard deviation. For really large sample sizes, if I had an n of 1,000 or 1,000,000, I mean, S is basically going to be the same as sigma, right? My sampling error is going to be very, very small at that point, and estimating sigma by S, I have a very good estimate of my standard deviation at that point. So for large degrees of freedom, my t distribution will be really close to z. Its tails will be a little bigger than z, and its middle area will be a little smaller than z. But in blue here, we have like t with large degrees of freedom. Maybe something like 50 or 100 degrees of freedom. It's basically sitting right on top of z with even maybe 30 degrees of freedom. It's pretty indistinguishable. But what if I have a smaller number of degrees of freedom? Well, then I end up with much bigger tails than z. And not just bigger tails than z in the way that you might have like a normal distribution that has a bigger standard deviation. It's not like z is a normal distribution with standard deviation 1 and maybe t is a normal distribution with standard deviation 2. It's like fundamentally bigger. The way that the tails go to 0 is polynomially. It's like, negative x squared or something like that, rather than exponentially or even super exponentially. So this might be like a t distribution with degrees of freedom, I don't know, 10 or something like that. Fundamentally heavier tails. The tails go to 0 kind of fundamentally slower than z. They don't go to 0 exponentially fast. They go to 0 like polynomially fast. Something like 1 over x squared, kind of a deal. Or if I had a pretty small degrees of freedom, maybe degrees of freedom 5 or something like that, then my t distribution would look even, it would have even heavier tails. even less mass concentrated towards the middle. Because if I have this small of a sample, 4, 5, 6 elements in my sample, not only is X bar observed probably not that great an estimate of mu, just because there could be a lot of sampling error, but also S is probably not a particularly good estimate of sigma, again, because there's the chance for a lot of sampling error here. This is saying nothing about representative samples or anything like that. We're not taking that into account here, just the sampling error and estimating these things. So the t distribution kind of looks like the standard normal distribution. It kind of functions a similar way. It's still symmetric about 0, just like the standard normal. It even has the similar shape as the standard normal. If you graph, say, 1 over 1 plus x squared, you'll see that you get a shape that looks like a normal distribution. In fact, we can do that really quickly. I'll just do it over here. You don't have to follow along. We're not really. Well, but just to show you that that's what it looks like. 1 over 1 plus x squared. And on window, let's go -2 to 2. And yeah, that's probably fine. So you can see that it looks, I mean, it's a kind of a funky window, but you can see that it looks kind of like a normal distribution. But it really seems like it's kind of squatter and wider fundamentally than a normal distribution. It doesn't have that nice, like, sharp curve down in the middle like a normal distribution tends to have. Okay, so we're not going to go through the derivation of how the t distribution works or like why the t distribution is the right distribution to use here. But we're just going to make the statement that we can replace sigma by s in our, all the way back up here, in this distribution, confidence interval for the mean when standard deviation is known, when we have the z distribution at play, when sigma is known. If we come down here and replace sigma by s, it turns out that just the right distribution to use to account for this extra variation in estimating 2 things instead of just 1, turns out the right distribution to use is exactly the t distribution. So the extra penalty that I pay, so to speak, for not knowing the population standard deviation and having to estimate it as well is that I have to use the t distribution, which is squatter and wider, which means to get a small area in the tail, I'm going to have to go further out. I'm going to have a wider confidence interval. To maintain the same level of confidence, I'm going to have to report a larger swath of the real line to maintain that level of confidence because of the additional variability in the system from estimating 2 things instead of 1. So, I mean, it's not just like somebody said, the t distribution looks like the normal one is a little wider. Let's just use that one. There's, a bunch of math that supports this, that like this is exactly the right distribution to use. But that's just beyond the scope of this course. A little bit later, probably not today, maybe next time, or I might refer you to a previous lecture recording for this. We'll look at some line fit plots, some QQ plots for, basically asking the question, what if I did this and kept this as Z? Would that work? And we'll see that, things don't really line up right. And then when I say, what if I do this and change it to T, things line up a lot nicer. So that'll be our empirical evidence to support this claim, because this is a claim that we are not giving theoretical support for. So we'll look at that probably next time. Okay. So that is all the theoretical background I wanted to say. The next thing that we need to be able to do is to look up T numbers. So I'd like to be able to look up, switch away from red pen there. There we go. I'd like to be able to look up, for instance, like T.05 or something like that the analog to looking up, say, Z 0.05. I have a Z table that I use to look up Z scores. And what I posted in chat earlier, the T table, I use that to look up T values. So this is in your book. It's in the back of the book in one of the appendices. But I also posted it on Blackboard and shared it in the chat, so you can find it in any of those places. And this is what the T distribution table looks like. Note that here we kind of take both the left and the right tails with one table. So we're leveraging the symmetry here. We're saying the critical T value, the T index, if you leave the answer that you get from this table positive, that's the right tail answer. And if you make it negative, that's the left tail answer. So there's a little bit more of an expectation on you to respect the symmetry here and to decide whether your T number ought to be positive or negative, your T index. Right? We had some practice at that with Z, right? So we would just say, oh, okay, well, the table gave us a negative Z index, but we know we need to flip that to positive. And so we need to do that with the T index here as well. But one challenge that we have with T is for standard normal for Z, for this guy, there's exactly one standard normal curve. There's exactly one standard normal distribution. It's the normal distribution with mean 0, standard deviation 1. I can give you a table for that where you can look up indices on the outside and find probabilities on the inside, and that's that. But I've got a bunch of T distributions parameterized by this nu. These are even like kind of standard T distributions, basically. But there's a whole family of standard T distributions. There's one standard normal distribution, but there's a whole bunch of standard T distributions. There's one for 1 degree of freedom and one for 2 degrees of freedom and a different one for 3 degrees of freedom. So if you wanted, to have information about information that looks like this, that looks like the Z-score information for your T distributions, if you wanted 30 different T distributions, 30 different degrees of freedom to be able to look up, you would need 30 pages front and back like this. One of them would be like negative T scores and the other one positive T scores, and they would be associated with a T distribution with 1 degree of freedom. And then you have another page for T distribution with 2 degrees of freedom, and yet another for T distribution with 3 degrees of freedom, and so on. If we were looking up probabilities related to the T distribution, like we were when we were doing, say, central limit theorem problems or normal distribution problems in chapter 6, we absolutely would need that. We would need a book of tables for T distributions, and it would be super annoying and cumbersome and all of that. But we're not actually looking up probabilities related to the T distribution, right? We only need T indices. And for that matter, in our confidence level, our confidence intervals, we're almost always just using 90%, 99%, or 95%, 95% being the most common of all of them, intervals. Right? I mean, when I was looking up my Z numbers, I was quite often ending up either here, or maybe at 0.0250, wherever that is, at this one here, right? I was really just plucking out the same handful, 3 or 4 Z indices over and over for my confidence interval questions. So like most of this, like this whole information up here, or like all of this information down here, this is all useless as far as confidence interval information go, right? I'm essentially never looking for a 92.37% confidence interval. We just don't do it. I mean, we could in theory, but we just don't. We ask for a 90% confidence interval, 95 or 99% confidence interval, something like that. So I really only need a few pieces of information. related to, say, this area and this index, or maybe this area and this index, right? There's only 3 or 4 pieces of information I need for each of my distributions. And that's what this table gives us. It says we have two tail areas. So area combined between the two tails of, say, 5%, maybe related to a 95% confidence interval, or 1% related to maybe a 99% confidence interval, or 10% related to maybe a 90% confidence interval. And it gives me, with areas input, it gives me output in the middle here that is a t index. Note that this t table is set up the opposite of the normal table. The normal table had z indexes on the outside, and it had probabilities or areas on the inside in the field of the table. This has areas at the top here in this index row, and it has t indices, values along the t-axis on the bottom here, that are in here. So, like, you know, the area to the right of 5% is in a, say, t distribution with 8 degrees of freedom. An area to the right of 5% is associated with a t index of positive 2.306. Or an area to the left of 10% in a t distribution with 12 degrees of freedom, an area to the left of 10% would be associated with a t index of, well, negative, because it's a left area, negative 1.782. So I look up my area at the top here, my degrees of freedom coming down the left, and then I find my t index in the middle. So this table works the opposite of the z table. But you notice that we have one row that relates to the 1 degree of freedom t distribution, another row that relates to 2 degrees of freedom t distribution. We're getting maybe something in the ballpark of 40 or 50 different t distributions information here on a single page, because we only need a very small amount of that overall information related to the distribution to be able to do our confidence interval calculations. You might even, this is kind of a side note, but you might even note that down here where it says large degrees of freedom, where some places, some tables will say just have a little infinity sign there. 2.58, 2.33, 1.96, 1.645. These numbers sound really familiar, particularly maybe 1.645 and 1.96. These are exactly the z numbers. Remember, I said that as the number of degrees of freedom gets very large, t converges to z. We can actually use the t table to kind of cheat and look up our z indices really quickly. Instead of using the normal table, this is a little bit of a side note. Instead of using the normal table, which we have to like find the area in that big field of numbers, is kind of hard to track down, and then find our z index, we could just come in here and say, okay, I want 90% confidence interval, area combined between the two tails is 10%. My z number, 1.645, z index. 95% confidence interval, my z index, just go all the way to the bottom, 1.96. So nice little time save there if you're interested in that. If you're not, you can just use the z table to find the z stuff and leave it at that. But in some tables, instead of saying large degrees of freedom or infinite degrees of freedom, some of them will just have like a little z down here, just indicating, yeah, these are just the z numbers. Okay, so that's how we find the t index. We need two things. We need the area to the right or left, and we also need the degrees of freedom, right? We need that as well, so we know which t distribution we're on. So we know which line we're on, and then we can find out which column our relevant index is in. All right, so let's look at an example. Suppose body temperatures are normally distributed. We're assuming this because we have a small sample size, and We still do need the central limit theorem to hold, actually, even though it might not seem like it immediately because we're using t instead of z. So that's why we're assuming normal distribution here. A sample size 10 yields a sample mean of 98.25 and a sample standard deviation of 0.73, both measured in degrees Fahrenheit. Construct a 95% confidence interval for the true mean body temperature. And then we might want to answer a question like, does it seem feasible that people say the mean body temperature is 98.6 degrees? Does it seem that that could reasonably be the true mean body temperature for like the population of all people? Okay, so what do I know? And what don't I know? Well, I don't know mu, obviously, because I wouldn't be trying to estimate mu if I knew it. I would just say what it is. But here I also don't know sigma. What do I know? I know X bar observed is 98.25. I know S, my sample standard deviation is 0.73. I want to be careful. Okay, sample standard deviation. So I could be given this information as standard deviation or as variance. So I just want to check that I am in the right, that if I'm given standard deviation, then I'm calling it standard deviation, and if I'm given a variance, I'm calling it variance. So double check that. That looks good. I know my sample size as well. So I know all of my sample stuff. N equals 10. N equals 10 means my degrees of freedom, 10 minus 1, my degrees of freedom are going to be 9. So that's that tells me which t distribution I'm on. I'm on the t distribution with 9 degrees of freedom. That's a different distribution than the t distribution with 7 or t distribution with 12 degrees of freedom. The same way that a normal distribution with a mean of 10 and a standard deviation of 12 is a different distribution than a normal with a mean of 5 and a standard deviation of 20. Right. I know that my confidence level, I want a 95% confidence interval, so confidence level 95%. This tells me I need a little more space here. This tells me that alpha is 5%, and this is the 2-tail alpha. So this is the total area between the two tails where sometimes I miss low and sometimes I miss high. And alpha over 2 is 2.5%. This is the 1-tail alpha, so 2.5% in each of the tails. 2.5% of the time I'll report an interval that's a bit too low, and the actual mu will be above the upper bound for my interval, and vice versa. 2.5% of the time I'll report an interval that's a bit high, and my actual mu will be below the lower bound, for a total error rate of 5%, 2.5% in each tail. Okay, so I see that my confidence interval setup is basically the same. It's my point estimate plus or minus the margin of error, and the margin of error is an index of a probability distribution times the standard error. So I have my lower and upper bounds. They started the point estimate, X bar observed 98.25, plus or minus or plus a t number. Let me come back to that. So this is going to be t alpha over 2 times the standard error. Well, here my standard error is just s over root n. S is 0.73 over root 10. Now t alpha over 2, to compute that, again, degrees of freedom are 9. And my 1-tail alpha is 2.5%. My 2-tail alpha is 5%. Notice on the table over here, it gives us both 1-tail alpha and 2-tail alpha at the top. So I like to actually compute both of them So I know I'm looking for the column with 2.5% and 5% in it, right? If I just did a two-tail alpha of 5%, I might mistakenly grab this 5% and start looking down this column and not realize that that's actually the one-tail 5% alpha, not the two-tail 5%. So if I know both of them, if I know my two-tail alpha is 5%, one-tail alpha is 2.5%, very clearly in this column here, we actually see that it's bolded because it's the most commonly used one, 95% confidence interval. So we're looking down this column, and we're looking for the degrees of freedom 9 row. So we're looking across this row, and I see that I have 2.262 as my t index. So I have to go 2.262 standard errors away from the mean in either direction to get a 95% confidence level. Let me come over to my calculator. And 98.25 minus. And from this point forward, it's going to feel just like the previous setup, right? Really, the big difference is just in the computation of this t index. Otherwise, it feels just like the previous confidence intervals. 2.262 times 0.73 over square root of 10. Little bit of a funny story. Square root of 10 is very close to pi. So let me finish this up and then I'll say why that's true. So this gives me about 97.7 for the lower bound and about 98.8 for the upper bound. So my 95% confidence interval for mu, the true mean body temperature of the population, 97.7 to 98.8. That is my confidence interval. It's a little wider than it would have been if I had known, for instance, that sigma was 0.73, because then I would have been able to use a z index 1.96 here, going from 1.9 to 2.2. That's a jump of about 0.3 units on a scale of 2. So that's what, maybe a 15% increase. So my interval is maybe 15% wider, and that accounts for the extra variability from estimating the standard deviation by the sample standard deviation, in addition to estimating mu by sigma x bar, or mu by x bar observed. Little kind of tangent, square root of 10 is very close to pi. Whoops. Square root of 10. You can see it's pretty close to pi, 3.14 or so is pi. And that actually is also 10 is, or pi squared is really close to the gravitational constant in meters and seconds and so on. And that actually has to do with the length of a pendulum, and it's a bunch of really cool math that's all tied together. So if you're, nerdy and into that kind of stuff, if you find physics and stuff interesting and science, look up, like something like, y is pi squared equal g or something like that. Or like, pi gravitational constant and pendulum or something like that. And you'll find a write-up. I'm sure there are a bunch of them online, people that have done a write-up on why that's true. But it has to do with the length of a pendulum, saying, okay, if the length of a pendulum arm is 1 meter and we have a ball at the end and we let it go and we say that the time it takes to go over and back is 1 second, back in the day, they didn't have atomic clocks and things. So this might be how they would explain to people far away, like, how do you know that your 1 second is the same as mine? Well, if you know how to determine a length of 1 meter, then do this with a pendulum, and the time that it takes to go over and back is what we all decide to call 1 second. So, anyway, I saw a square root of 10 and just reminded me of that. I think we'll leave this one for next time, so that we get, number one, a little more practice, coming back to computing a t distribution next time. before jumping into confidence interval for variance and standard deviation. And so we get, so we have a few more minutes to talk about one-sided confidence intervals. So far, every confidence interval we've done is a two-tail, where we could miss below or above. But what if we only wanted a one-side confidence interval where we only have one side that we could miss? It turns out that it's not that complicated to make that switch, but we just have to be a little careful about how we do it. So we'll talk about that when we come back, one-sided confidence intervals, get a little more practice with t-distribution in this problem, and then jump into confidence interval for variance and standard deviation. All right, let me stop the recording.